In this last video for today, we're going to see some uses for why we might ever want to recenter our Taylor series around something other than x equals 0. So let's take a look at this function, 3 over 2x minus 1, and we're going to write a power series for it. We're going to write it as a polynomial instead of a rational function. And you might remember from the first lesson of the unit, like, hey, that's an infinite geometric series. If we think of this as the sum of an infinite series with a1 over 1 minus r. And so we do have to recognize that the 1 minus r is a little bit backwards, so we would have to switch the signs of everything around, but that's not so bad. 1 minus 2x. And so we could think of that as a series with an a1 of negative 3 and an r of 2x. And so that would be the sum of negative 3 times 2x to the nth power, starting when there's no 2x and going on forever. And we can try that. We can go to Desmos and take a look at 3 over 2x minus 1 and compare that to negative 3 times 2x to the nth. And we can see, all right, well, there's just a linear approximation. We can see that nice little tangent line right there. But if we add more terms, it starts to follow, well, it does start to follow the curve, but it never really wants to go past that little spot there, right? We've got that little wagging tail up there, but we're not getting past there. Just getting a little tiny bit of time, but it's never going to go much farther than that. On the other end too, it's not really going anywhere past here where we need it to go. And we saw this with the geometric series turned into power series, that there's an interval of convergence. There's only so much values for x where this actually holds. And so let's say I didn't want the series to only be around x equals 0. What if I wanted to use a Taylor series to find the values for x somewhere around here, around x equals 2? And that's why we need to have this ability to move the center of our Taylor series over. It didn't really matter so much for sine, because sine doesn't have an interval of convergence, or it does, but it's infinite. It works forever. Not all functions are like that. And so that's why it's useful to be able to center around x equals anything other than 0. So we're going to try this again, but this time we want to see an x minus 2 in our denominator. We want x minus 2 to be that thing that repeats, because remember we saw that with the power series for the sine evaluated when x equals pi over 2, that we see the x minus a show up over and over again in those parentheses. So we want this to be x minus 2, not just 2x. Well, we can do that. Keep in mind that if there's a 2x here, it would have to be 2 times x minus 2, or 2x minus 4, which means I want to see a 2x minus 4 here. Okay, well, if I want that to be 2x minus 4, what I can do is rewrite that as 2x minus 4 plus 3. You can think of this in a couple of ways. You can say, well, if I want this negative 1 to be a negative 4, I just need to subtract 3. But if I'm going to subtract 3, I have to also add 3. I can't just subtract 3 whenever I feel like it. So I need to balance that out by also adding 3. And then I can rewrite that as 3 over 2 times x minus 2 plus 3. And we're starting to see our x minus 2 show up in the spot where that common ratio of our geometric series appears. The only thing is we've still got the slight little problem here. That's supposed to be a 1, not a positive 3. But that's an easy fix. We can just divide everything by 3. So divide all terms in both numerator and denominator by 3. So we've got 1 over 2/3 times x minus 2 plus 1. And now we've got the 1 that we're supposed to see from the a1 over 1 minus r. And so now we can identify the a1 is 1, and the r, be careful about this one, it's supposed to be 1 minus r, but everything in that denominator is positive, which means that the r must be negative 2/3 times x minus 2. And so I can rewrite this as the geometric series. Start from n equals 0 and go until forever of a1 times my common ratio to the nth power. And I can just ignore that little 1 there because it doesn't really do anything for me. And there's my series. Negative 2/3 times x minus 2 to the n. Notice how the negative 2/3 is in the parentheses being raised to the nth power also, because it is part of the common ratio. So that was the one that didn't work so well. So I'll turn that one off. And down here I've got another one. Negative 2/3 times x minus 2 to the nth. Let's take a look at that one. And this time it is matching our red function perfectly again. And this time it's doing it in the spot where we wanted it to, right around x equals 2. Now notice it still doesn't have a permanent or an infinite interval of convergence. And in order to figure out what that interval of convergence is, we need that common ratio, which we said already over here was negative 2/3 times x minus 2, to have an absolute value less than 1. And so we can solve that using the absolute value inequality we learned back in Algebra 2. Turn that into a compound inequality. Negative 2/3 times x minus 2 has to be less than 1, and negative 2/3 times x minus 2 has to be greater than negative 1. That's what it means to have an absolute value less than 1. When we solve this inequality, think back to Algebra 1 here. Don't forget to flip that inequality symbol over when we divide both sides by negative 2/3. And on the other side, x minus 2 has to be less than positive 3/2. So if we add 2 to one side, x has to be greater than, I'm sorry, this should be negative 3/2. X has to be greater than 1/2. And on the other side, add 2/2 to 3/2. That's 7/2. X has to be less than 7/2. So our interval of convergence is that x has to be between 1/2 and 7/2. And if we just take a quick look at our graph, we can see that that seems to be where our equation is matching up. Everything from 1/2. You can see that vertical asymptote here. X is 1/2. Seem to be our blue Taylor series does seem to match the red curve pretty well up until that vertical asymptote. Not on the other side of it though. And it seems to be working again until right getting close to 3.5. Right there is where it starts to pull away. If we add a lot more terms here, we can see that it got even closer to 3/2, but it's never really getting there. Like that's as far as we're going to be able to match, even if we added an infinite number of terms.